Welcome to the fourth module of our Python Taster course. In this module, we shall program our robot car to follow simple and advanced instructions, including moving forwards and reversing, following black lines and routes, moving towards bright light sources, and automatically detecting and avoiding obstacles. In the last module, we built our ring bit car, and remember that it's the microbit that actually controls and drives the ring bit car. In order to program the microbit, and hence our ring bit car with instructions, we require a microbit code editor. An online-based microbit code editor enables you to develop the code for your program entirely within your internet browser. So the two most popular online microbit code editors are Microsoft MakeCode and the Python microbit editor. So Microsoft MakeCode is a visual color-coded block-based code editor for the microbit. And it's best suited for beginner programmers because it allows you essentially to drag and drop blocks of code onto the interface. And these blocks together will then make up your program, so there's no need to actually type any code. But the Microsoft MakeCode editor also supports JavaScript and Python text-based code editing. The Python microbit code editor is specifically for Python developers. So for the purposes of this taster module, we shall use the Microsoft MakeCode editor to develop Python programs for our ringbit car. To get started with Microsoft MakeCode and start developing programs for our microbit, hence ringbit car, first if you make sure that you've connected the microbit to your computer, use a USB micro B compatible data transfer USB cable. So once connected, if you fire up your internet browser and go to makecode.microbit.org, this will be the web page that's returned to you. Now, for the purposes of this taster module and this course, we highly recommend that you use either the Google Chrome or the Microsoft Edge internet browsers. And the reason for this will become apparent in a moment. So the next step, once you've gone to makecode.microbit.org, if you select New Project, and then give your project a name. So you can call it anything that you like. In our case, we're going to call it ringbit car, and then press the Create button. The default interface that's presented back to you is the visual color-coded block-based code editor for the microbit. So this essentially allows you to drag and drop blocks of code onto the interface, and together they will form the program for your microbit. Hence there's no need to actually type any code. However, for the purposes of this taster module, we want to write our programs for the microbit in Python. So if you go to the top of the window and select the drop-down menu and then select Python, this will change to the Python mode, and we're now able to directly enter Python statements into the online code editor in order to develop Python programs for our microbit. The next step is we need to import the Python libraries required to develop Python programs for the ringbit car. And to do this, we need to install an extension into the MakeCode editor. So if you select Extensions from the Options menu, and then in the search box, if you type in ringbit car and then search, we're going to install this first extension, so the Electfreaks MotoBit package for ringbit car. So if you select this extension, MakeCode will go away and install that extension, which again basically means it will import the required Python libraries to develop Python programs for the ringbit car. The final step in regards to setting up our environment is to set up a means by which we can transfer programs from our online code editor to the microbit that's connected to our computer via USB. Now, the process of transferring a program onto the microbit is called flashing, and there are essentially two methods of flashing available to us. So the first method is called the drag and drop approach. So this is where once you've developed your program within your online code editor, if you select the download button, this will then download a program file onto your computer, which you can then drag and drop onto the microbit device that's listed in your computer. Once you've dragged and dropped it, the program will then be installed on your microbit and run automatically. The second approach is called direct flashing. So direct flashing is where you transfer the program directly from your internet browser to the microbit via the web USB API. So there's no need to download, then drag and drop. You can transfer the program directly from your internet browser. So to set this up in MakeCode, if you select the three dots next to the download button and then select Connect Device, first it will prompt you to make sure that your microbit is actually physically connected to your computer. So if it's not already, please go ahead and connect your microbit to your computer using a USB micro B compatible data transfer USB cable. And once it's connected, if you select Next and Next, a window will appear listing the microbit devices connected to your computer. So if you select BBC microbits, then select Connect, and then select Done. So now your internet browser is now directly connected to the microbit via the web USB API. The microbit will also start making some noises in the background, as you can hear, and this is just to indicate that the connection between the internet browser and the microbit device is secure and complete using the web USB API. You'll also notice that the icon on the download button has now changed to a USB icon, indicating that direct flashing is now an option. So every time you select the download button, it will then directly transfer your program from your online code editor to the microbit. So direct flashing is much more convenient and also enables you to better test and debug your programs. So we recommended earlier that you use either the Google Chrome or the Microsoft Edge internet browsers, and the reason for this is at the time of speaking, only Google Chrome and Microsoft Edge, modern versions of those, support the web USB API. So if you're using a modern version of Google Chrome or Microsoft Edge, then you can proceed to use the direct flashing method. If not, and if you can't use either of those internet browsers for any reason, then you'll have to use the drag and drop approach, which is essentially download a file to your computer and then drag and drop it onto your device. In this example, our goal is to develop a Python program that will instruct the ring bit car to move forwards when we press the A button on the microbit board, to reverse when we press the B button, and to brake when we press both the A and B buttons at the same time. So you may recall in the last module when we built the ring bit car that we attached the microbit board to the ring bit board via the 5 screws. We also discussed the fact that the ring bit board is just a simple PCB or printed circuit board that extends the microbit's 3 GPIO pins P0, P1 and P2 and converts these to ground voltage and signal or GVS signal pins. We connected the left servo's jump wire to the GVS pins labelled 1VG. We connected the right servo's jump wire to the GVS pins labelled 2VG, and we connected the special expansion board jump wire to the GVS pins labelled 0VG. So the reason why it's important to remember this is that when we develop programs for our ring bit car, whether in Python or any language, we first have to initialize the wheels on our ring bit car. So what this means is we have to define into which of the microbit's pins the wheels are connected. So we connected the left servo's jump wire to the GVS pins labelled 1VG, and this corresponds to the microbit pin P1. And we connected the right servo's jump wire to the GVS pins labelled 2VG. This corresponds to the microbit pin P2. So going back to our example, let's start by initializing the wheels. So if you delete the default Python code in your editor, and we're going to initialize the wheels. So to do this, if you type in ringbit car, and remember that Python is a case sensitive language, so the ringbit car object starts with a capital R and a capital C. And then to initialize the wheels, we can write init underscore wheel. So the init underscore wheel method takes 2 parameters. So the first parameter is the pin in which the left wheel is connected. So if you type in analog pin.p1, which corresponds to the microbit pin P1, and the second parameter is the pin in which the right wheel is connected. So in this case, we type in analog pin.p2, which corresponds to the microbit pin P2. So that's all you need to do to initialize the wheels, and now we can get on with the actual logic of our program, which is, remember, if we press the A button on the microbit board, we want the car to move forward. If we press the B button, we want it to reverse, and we press both the A and B buttons at the same time, it should brake. So first of all, we're going to create a custom function that contains the instructions to execute when we press the A button. So custom instructions to perform when the A button is pressed. So if you remember, to define a function in Python, you use the def keyword followed by the name of the function. So in our case, we're going to call this function on button pressed A. So you can call the function whatever you want, but remember, ideally you want something short, concise and meaningful. So our function on button pressed A clearly conveys to other developers that this function contains the instructions to perform when the A button is pressed. So we want our car to move forward when the A button is pressed. So we want our ring bit car dot forward. So we can use the forward method to tell our car to move forward. Great. So we're going to create a second custom function that contains the instructions to perform when the B button is pressed. So custom instructions to perform when the B button is pressed. And again, so we're going to call this on button pressed B. So we want our ring bit car to reverse, and in this case we can use the back method to tell our car to reverse. And then finally we want a third custom function that contains the instructions to perform when both the A and B buttons are pressed at the same time. So custom instructions to perform when both the A plus B buttons are pressed. So again, def on button pressed, in this case A and B. So we want our car to brake when both the A and B buttons are pressed. So we want our ring bit car, and we can use the brake method to tell our car to brake. Great, so we have three custom functions that contain different instructions depending on which buttons are pressed. Now we want some way to link these functions to the actual event of pressing those buttons. So to do this, we want to bind the functions to something called input event handlers. So event handlers are special functions that are executed in response to a specific event or action. So in this case, the event is, for example, the button A being pressed, and when the button A is pressed, we want the event handler to execute the on button pressed A function. So we want to bind the functions to the relevant input event handlers. So to do this with the microbit, if you type in input dot on button pressed. So the on button press method takes two parameters. So the first parameter is the actual button that is pressed. So in this case, we're going to say when the A button is pressed. Then the second parameter is the code or the function to run when the A button is pressed. So in this case, we want to run the on button pressed A function. Similarly, we want it so that when the B button is pressed, then the on button press B function is executed. So again, type in input on button pressed, the button, in this case the B button, and then the code or function to execute when the B button is pressed. So in this case, on button press B. And then finally, when both A and B buttons are pressed, so we can do button.ab to denote both of those buttons being pressed. And then we want the on button pressed AB function to be called. So these are, again, event handlers. So these are functions that respond to a specific action. And in this case, the specific action or event is the button being pressed. And then you can invoke your code or function. Great, so that's our first example completed. So if we just recap. So first of all, we're initializing the wheels by telling our ring bit car which pins are connected to which wheels. So the left wheel is connected to the P1 pin, and the right wheel is connected to the P2 pin. We then have 3 custom functions that contain the instructions to perform when the relevant buttons are pressed. And then we bind those functions to the relevant input event handlers. So in response to button A being pressed, we run this function and so forth. Great, so now we're ready to transfer the program to our microbit board. So again, to do that, if you select the download button, and that will transfer it via direct flashing. Whilst it's being transferred, you'll notice that the yellow LED on the microbit board starts flashing, and that's fine. That's just to indicate that the program is being transferred. When it stops flashing, that indicates that the program has been successfully transferred, and the program will then be installed and run automatically. In this case, it will run in response to one of these buttons being pressed. In this example, our goal is to develop a Python program that will instruct the ring bit car to automatically follow a black line. So to follow this example, you'll need to have installed the tracking module on your ring bit car. So please refer to the previous module of this Python taster course for instructions on how to install the tracking module, ensuring that you connect the special expansion board to the ring bit board using the jump wire via the 0VG GVS pin, and that the ground wire is connected to the G pin. Please also ensure that the slide switch on the special expansion board is set to other modules in order to power the tracking module. So the first step is to initialize the wheels, which we've done here, so we can dive straight into the logic of our program. The next thing that we're going to do is we're going to define a new function called onForever. So the reasoning for this function name will become apparent in a moment. But inside this function, we want to define the instructions that will enable our ring bit car to follow a black line. So if you recall from the previous module, when we built our ring bit car and when we installed the tracking module comes with 2 infrared sensors, a left infrared sensor and a right infrared sensor. Now, in order to follow a black line, we need to follow the following logic, which is if the left infrared sensor detects deviation from the black line, then we want to stop the right wheel and slow down the left wheel in order for the car to turn right to continue to follow the black line. Similarly, if the right infrared sensor detects deviation from the black line, then we want to stop the left wheel and slow down the right wheel in order for the car to turn left and continue to follow the black line. If neither the left nor the right infrared sensors detect deviation from the black line, then that's fine. We can just continue moving forward. And it's this logic that we want to code inside this function. So the first condition that we want to test is whether the left infrared sensor detected deviation from the black line. So left infrared sensor detects the deviation from the black line, and if it does, we want to stop the right wheel and slow down the left wheel. Great, so the next challenge is how do we actually know whether the left infrared sensor has detected deviation from the black line? As it so happens, the ring bit car stores this information about its own state, and we can access this state information in order to conditionally execute these instructions. So to access this information, if we use the if conditional statement, followed by ring bit car dot tracking. Then to access the state information as to whether the left infrared sensor has detected deviation from the black line, we can type in ring bit car dot tracking state type dot tracking state 2. So it's tracking state 2, which tells us that the left infrared sensor has detected deviation from the black line. So if that's true, then we conditionally perform the following instructions. So we want to stop the right wheel and slow down the left wheel. So we need some way to control the speed of the respective wheels. So the ring bit car allows us to do this. So we can do ring bit car dot freestyle. So the freestyle method takes two parameters. The first parameter is the speed of the left wheel, and the second parameter is the speed of the right wheel. So we want to slow down the left wheel, so we're going to slow it down to a speed of 25, and we want to stop the right wheel, so we're going to have a speed of 0 for the right wheel. And then we're going to tell our car to pause just for a moment. So in this case, 250 refers to 250 milliseconds, or a quarter of a second. Great. So now we want to test the condition as to whether the right infrared sensor has detected deviation from the black line. So right infrared sensor detects deviation from the black line. If it does, we want to stop the left wheel and slow down the right wheel. Great. So very similar to before. So we can access this information about the ring bit car's own states, but in this case, tracking state 1 refers to the state that the right infrared sensor has detected deviation from the black line. And if it has, then again we can use the freestyle method, but in this case we want to stop the left wheel, so we put a 0 as the first parameter, and we want to slow down the right wheel, so we're going to slow down the right wheel to 25, and again we will pause it momentarily. Great. So now if neither the left nor the right infrared sensors detect deviation from the black line, then we just want to move at normal moving speed. So again, we can use the freestyle method. So if we previously slowed it down to 25, then the normal speed, let's say we set them at 50. So since we're setting both the wheels at the same speed, this is essentially telling the ring bit car to move forward. So we could have used the forward method, or in this case we're using the freestyle method to control the speed, but the ring bit car will still move forward. So now that we have the most complicated part of our program developed, which is the ability to detect deviation from the black line and take action accordingly, we now want to bind this onForever function to some event or action. So we're going to create a new function called onButtonPressedA. So similar to the previous example, this will contain the instructions to perform when the A button is pressed on our microbit board. So the first thing that we're going to do is we're going to instruct the car to move forwards when the A button is pressed. So to do this, we're going to use the freestyle method again. So we could use the forward method, which would instruct the car to move forward at full speed. With the freestyle method, and if you set both wheels to the same speed, this will again instruct the car to move forward but at reduced and controllable speed. So the next thing we're going to do is something new. So we want our ring bit car to follow a black line or a route indefinitely. So it will never stop unless the batteries run out or you turn off the microbit board. So we want to run a given function continuously in something called a forever loop. So as the name suggests, the forever loop will just run indefinitely until you turn off the microbit board. So to bind a function to a forever loop, we can type in basic.forever, and then the forever method takes the code or the function that you want to run continuously. So in this case, we want to run the onForever function code indefinitely. Great. So again, this method will contain the instructions to perform when the A button is pressed. So when we press the A button, the car will start to move forward, and then it will forever follow the instructions in this function, which is it will continuously detect deviations from the black line, and if it detects deviations, it will take the appropriate action. If it doesn't detect deviation, then it will just continue moving forward. So the final thing we need to do, as in the previous example, is bind this function to an event handler. So in this case, we want this function to be invoked when the A button is pressed. So again, as in the previous example, we can do on button pressed. The first argument is the button that we are interested in. So in this case, the A button. When that is pressed, then it will run the on button pressed A function. Great, so that's our program for following a black line. So just to recap, so we've initialized the wheels as before, and then we've defined a custom function called onForever, which detects deviation from the black line and takes action accordingly. If no deviation is detected, then it will just continue to move in a straight line, albeit at a slower speed. We then defined another function that contains the instructions to perform when the A button is pressed on the microbit board. So when the A button is pressed, it will start to move forward, then it will forever, in a forever loop, execute the code in the onForever function. Hence the reason why this function is called onForever. And then finally, we bind this function to the button A press event. So as soon as we press the button A on the microbit board, the ring bit car will start to follow the black line indefinitely. In this example, our goal is to develop a Python program that will instruct the ring bit car to follow a light source. Now for this example, there's no need to install any additional add-on modules or additional hardware. The detection of the light levels is actually achieved through the LEDs on the front of the microbit board. So the first thing we're going to do, as before, is to initialize the wheels. Then we're going to define a new function called onForever. So if you followed the previous example, you'll know that the instructions that we're going to develop within this function are designed to be run indefinitely. So we want to check whether the light level is greater than a certain threshold using a comparison operator that we studied in the second module of this Python taster course. So if the light level is greater than a certain threshold that we can define, then we want the ring bit car to move forwards towards the light. Otherwise, if the light level isn't greater than this certain threshold, then we want the car to stop or to brake. So we want to check the light level using a comparison operator. If the light level is greater than n, which we can define ourselves, then move forwards towards the light. Otherwise, brake or stop. So how do we actually access the light levels that have been detected by the LEDs on the front of the microbit board? So again, we can access this information. The ring bit car stores this information. So the light levels are a type of input. So we can use the if conditional statement, input.lightLevel. So the light level method will return the levels of light detected by the light sensors, and this will be a number. So 0 will refer to complete darkness, all the way up to 255, that refers to bright white light. So we want to say if this light level is greater than, using the greater than comparison operator, a certain number. So let's say we want to set this to 40. If the light level is greater than 40, then we want our ring bit car to move forward using the forward method. And if it's not greater than this threshold, we can use the else branch and tell our ring bit car to brake or to stop. And that's the logic of the onForever function. So again, we're checking the light level, we're accessing the light level using the input.lightLevel method. And if it's greater than a certain threshold, in this case 40, we want the ring bit car to move forwards towards the light. Else, if this condition evaluates as false, then go to the else branch and tell the car to stop. So finally, we want to run this function indefinitely in a forever loop. So as in the previous example, we can use basic.forever to tell our ring bit car to run this function forever in a forever loop. Great, so that's our program. So just to summarize, so we have first initialized the wheels as before. We've then defined a new function called onForever that's going to store code that's designed to run indefinitely. So within this function, we're detecting the light levels, and if it's greater than a certain threshold, then we tell the car to move forward. Otherwise, else we tell the car to stop. And then we bind that function to a forever loop so that it runs indefinitely. In this example, our goal is to develop a Python program that will instruct the ring bit car to automatically detect and avoid obstacles. So to follow this example, you'll need to have installed the sonar bit module on your ring bit car. So please refer to the previous module of this Python taster course for instructions on how to install the sonar bit module, ensuring that you connect the sonar bit module to the ring bit board using the jump wire via the 0VG GVS pin, and that again the ground wire is connected to the G pin. Now, before we start coding, we need to install another extension into MakeCode in order for it to import the required Python libraries in order to utilize the sonar bit module. So if you select extensions, now the extension that we want to install isn't directly available via MakeCode. So in the search box, we need to access it via its GitHub code repository. So if you type in https followed by github.com/elecfreaks/txt sonarbit, and then press enter or search. So this is the extension that we want to install, which is called sonarbit. So if you select that extension, MakeCode will go away and import the Python libraries required to utilize the sonarbit module, and you'll also see the sonarbit has now appeared in the options menu. Great, so now we can start developing our program. So the first thing we're going to do is initialize the wheels as before. So hopefully this should be familiar now. So ringbit car.init wheel, and the first parameter is analog pin.p1, and the second parameter is analog pin.p2. Next, we're actually going to define and initialize a variable. So we're going to initialize the sonar variable. So we're going to create a new variable called sonar, and we're going to initialize this with the value of 0. So I'll talk more about what this variable actually means in a moment. Next, we're going to create a new function called onForever. And as with the two previous examples, this will contain instructions that are designed to be executed indefinitely. So, going back to what we want this example to do, we want our ringbit car to be able to automatically detect and avoid obstacles. If you recall from the previous module, when we built the ringbit car and installed the sonarbit module, the sonarbit module is actually an ultrasonic sensor that sends out pulses to detect distance to objects. And it's capable of detecting distances up to 4 meters. So we want to be able to access that distance that's detected by the ultrasonic sensor. And then we want to do some conditional logic on that distance, such that if that distance is less than a certain threshold, then we want our ringbit car to automatically turn and move to avoid the obstacle. Otherwise, if it's not less than a certain threshold, then the ringbit car can continue to move forward. So the first thing we want to do is read the distance in centimeters to an object detected by the ultrasonic sensor. And we want to store that distance in the sonar variable that we defined earlier. So store that distance in the sonar variable. So first we're going to write global sonar. So this is saying that when we overwrite the value assigned to the sonar variable, we actually want to overwrite the variable that's defined outside of the function body, so the global variable called sonar. So how do we actually access the distance that's been measured by the ultrasonic sensor? So we can go sonar is equal to sonarbit.sonarbit distance. Then the sonarbit distance method takes 2 parameters. So the first parameter is the unit of distance that we want it to measure. So we want it to measure distances in centimeters. So we can do distance underscore unit dot distance unit centimeters. So it will return the distance measurements in centimeters. And then the second parameter is the microbit board pin in which the sonarbit module is installed. So recall that we've installed the sonarbit module into the 0VG GVS pin that corresponds to the microbit pin P0. So as a second parameter, we're going to write digital pin.p0 to refer to the pin P0. Great, so this statement has allowed us to retrieve the distance in centimetres that's been recorded by the ultrasonic sensor. Next, we're going to simply just display that current distance measurement on the microbit board utilising its LEDs. So we're going to display the current distance on the microbit board. So to do this, we can use basic.showNumber, and the showNumber method basically takes one parameter, which is the number that you want to display on the microbit board. So in this case, we want to display the value of sonar, which is the distance measurement that we've accessed in the previous statement. So we now know the current distance that's being measured by the ultrasonic sensor, and we're displaying that on the microbit board. Now we actually want to do the actual object avoidance. So we want to say if that distance is less than a certain threshold, and again we can define what that threshold is, then turn to avoid that object. So if the distance to the object is less than n centimeters, and again we can define n, and is not 0 centimeters. So if the distance is 0 centimeters, then obviously it's already hit that object. Then avoid the object by turning. Otherwise, continue to move forwards. So to do this, we can use comparison operators, and because sonar is being assigned a numeric value, it's very simple just to say if sonar is less than a certain threshold. So in this case, we're going to say if the current distance to the object is less than 15 centimeters in this case, and sonar is not equal to 0, so it hasn't already hit the object. So if it's 15 centimeters or less away from the object, then we're going to instruct the ring bit car to turn. And again, to instruct the ring bit car to turn, we can use the freestyle method to control the speeds of the wheels. So the first parameter is the speed of the left wheel. So let's say we want to stop the left wheel, and then the speed of the right wheel, let's say 50. So this will cause the ring bit car to turn left upon detecting an object less than 15 centimeters away. And then we're going to tell it to pause briefly. So in this case, 500 milliseconds or half a second. If the distance isn't less than this certain threshold, in this case 15, then we're just going to instruct the ring bit car to continue moving forward at a slower pace than full speed. So again, we're going to use the freestyle method and provide the same number for the speed of the left wheel and the right wheel. In other words, move forwards but at a reduced speed. Great, so that's the logic of our onForever function. So we've extracted the distance that's been detected by the ultrasonic sensor in centimeters, and then we've displayed that on the microbit board. And then this is the main logic of the program. So if the distance is less than a certain threshold, in this case 15 centimeters, and if it isn't 0, i.e. if we haven't already hit the object, then instruct the ring bit car to turn left using the freestyle method by controlling the speeds of the wheels. In this case, stop the left wheel and move the right wheel at speed 50, causing the ring bit car to turn left. If the distance isn't less than this threshold of 15 centimeters, then the ring bit car can safely continue to move forwards. Great, so now that we've defined our onForever function, again let's bind it to a forever loop so that it will run indefinitely upon someone pressing the A button. So we can do create a new function called on button pressed A. And so when we press the A button, we're going to instruct our car to start moving forwards. So ringbitcar.freestyle to move forward at a reduced speed rather than full speed. And then we're going to bind this on forever function into a forever loop using basic.forever, then the code or the name of the function. Great. And then finally, again, as with the previous examples, we're going to define an event handler such that when the A button is pressed, it will invoke the on button pressed A function. So again, to do this, input.on button pressed. The button, in this case, when the A button is pressed, then invoke the following code, which will tell the microbit car to move forward and then indefinitely execute this code, which is the actual object detection and avoidance. And that is our full program. So just to recap, we are initializing the wheels as normal, and we've initialized a variable called sonar. We've then created a new function called onForever that's going to contain the instructions to run indefinitely. And inside this function, we are detecting the distance to an object in centimeters that's detected by the ultrasonic sensor. And we're storing that in the global sonar variable. And then we display that current value assigned to the sonar variable on the microbit board using the showNumber method. And then the main part of the program is if that distance is less than a certain threshold, in this case 15, and if it's not 0, then instruct the ringbit car to turn left. If the distance isn't less than this certain threshold, then it can safely continue to move forwards. And then we've defined another function on button pressed A, which is to start moving the car upon pressing the A button, and then bind the onForever function to a forever loop such that the object detection and avoidance is done indefinitely. And then finally, we define an event handler such that when you press the button A, then this code is invoked.